Hi, everyone. We'll get started in just a minute. We have a special guest, James from IBM Quantum Education. So if you all just want to kind of post in the comment section again where you're coming from, that'd be awesome. So James can see where everyone's from.
Well, everybody's typing really fast. And they're from everywhere, literally everywhere.
So we'll get started while people are still filtering in. Hi, everyone. Welcome to our Introduction to Quantum Computing course with IBM Quantum. So excited to have you here today. This will be the beginning of our lecture series on mathematics for quantum. So you might have been wondering earlier in the semester why you were learning all these different math concepts. Today, it will start to make a lot more sense, the importance of those math concepts like matrices and vectors for quantum computing. So we're going to start getting into the quantum aspect of the course, which I know you all are very, very excited for, and we're excited for as well. Before we get into the lecture by Amir, I wanted to introduce James, who is on the IBM Quantum Education team. So he's going to discuss QxQ blocks, which is some fun educational activities that you can do over winter break to stay engaged in the weeks while we're off in session. So with that said, James, I'll turn it over to you.
Oh, hi. Yeah, thank you very much for the introduction. Yeah, I've got approximately 15 minutes to show you this really fun game. It's a Minecraft-like game that you can go in and play with quantum computing circuits. And so I'm going to go ahead and get started and show my screen here. And this is a presentation that I typically give when I'm showing people QxQ blocks, and it's a whole presentation on quantum computing. And I know that you've been doing a lot of studying already, and so there's a lot of things I can skip and get right into the fun stuff. So these slides are at a link that I believe was given to you all at QxQ.it/blocks. And if you go to that link, you'll see my my GitHub repository for the code for QxQ blocks, and it also shows you how to install and run it. There's also a nice video in which I give a presentation, you know, like almost an hour-long presentation on quantum computing and QxQ blocks. So this next 10, 15 minutes is just going to be kind of a let's play video about this. So a little bit about me. My name is James Weaver. As was said, I'm a quantum developer advocate and a Java champion at IBM Quantum. I've written several books, mostly on Java and Raspberry Pi and JavaFX and some subjects like that. And I'm going to go straight to this game. And so assuming that, you know, like when you go in and install this thing and run it, then you'll see something like this. And you'll go in and, you know, create a new world and play your game here. And this is a lot like Minecraft. It's an open source version of Minecraft called Minetest. And it's also got some ideas from Portal. And so when you go into the world, there's a lot of things to explore outside this door and different places like riding that mine cart. But what I'm going to do, I'm going to go straight into these Portal escape rooms. And to do that, I'm going to go into this TARDIS. This TARDIS, inside the TARDIS is actually a portal hub. And so I'm going to leave this room where you can, you know, learn a lot about circuits and gates and things like that. by right-clicking on these help signs. I'm going to leave this room and I'm going to go straight into this TARDIS that has this portal hub. And I'm going to jump into the level 1 of the escape rooms here. And it's real important to read what's showing on the upper left-hand corner of the screen, because what's showing there is what Professor Q is coaching you through. She's interested in helping you get through these escape rooms. So this first clue up here, up on the upper left, says it asks you in the last sentence to change the quantum state of the circuit from 0 to the state shown on the wall. And so just like with Portal, you know, we look around the room and we see what's going on here, and we see this state on the wall. And that state is a 1 state. It's a 1 qubit, a qubit with the value of 1. And this liquid-filled block here means you want the 1 to have a probability, 100% probability, because the liquid block is filled. You want this circuit to make it 100% probability that when the circuit is run, that the 1 will be measured. And so right now it's exactly the opposite. If we ran this circuit, there's a 100% probability that the result of measurement would be 0. And so looking around the room, let's see, we see a door. In order to leave, I'm going to have to solve this puzzle for that door to open. And what else do we have in the room? Well, we have a chest. So I can right-click on that chest, and I see that there's an X block. That's an X gate. It's a quantum X gate. So I'm going to wield that block and right-click on the circuit, and you'll notice that this Q turns gold, and that the liquid is completely full above the 1. So when this is measured, whenever this is measured, it's always going to be a 1, because it took this 0 and it applied an X gate or a NOT gate and made it so that the value is 1. And so every time I measure it, it's going to be 1. Also, the door opened. And now we can go through to the next puzzle. Look on the wall, and it says that the state that we want is 1, 0. 100% probability of 1, 0 when we measure it. So right now, we're starting out with 0, 0, because coming in is 0, 0, with the left qubit there being the one on the bottom wire, and the right qubit being the one on the top wire. It's color coded. So if I wanted the state to be 1, 0, then I would need to put an X block on this wire, and that would turn the 0, the magenta 0, into a 1. So I'll give that a try. I'll go to the chest, right-click it. Sure enough, there's an X gate. And then we'll go over here and we'll put the X gate on that bottom wire. And notice that we have 100% probability that 1, 0 will be the result of the measurement. And I can right-click these spheres here, and we see that it's always 1, 0. So then the door opens. The door happened to be behind the circuit here. And then we have another puzzle, and that's a state of 0, 1, 1. We want a 100% probability that it'll be 0, 1, 1 when we measure it. But right now it starts out at 0, 0, 0. And again, this is more of the same. When I look here, I'll see an X block, an X gate, and then I can go here and let's see, it's 0, 1, 1. So to solve that one, I'll just right-click this wire and that wire, and we see 0, 1, 1. Now you might notice, and you might have already known this, but since we have 3 qubits, 3 wires, there are 2 to the 3rd basis states that it could possibly collapse to when measured. And so by putting the X blocks on these 2 wires, then we end up with 100% probability of this basis state being selected, 0, 1, 1. And so now the door is behind us, and so I need to just go up that ladder. Need to be careful not to hit that portal, because I'll go into the portal room. But we'll go up to the ladder, go up to the other side. Didn't go high enough there. There we go. And so now those first 3 puzzles were all classical. They were all just not gates, and the results were just binary. But now this will be the first puzzle that is not classical, it's quantum. So if I look at the clues up at the top, it says this room is where Schrodinger's cat starts getting nervous. Put the qubit in an equal superposition of dead and alive, or of 0 and 1. And so now this puzzle's a little different. So if I look on the wall, then I see some Dirac notation that indicates that I need to make this circuit have a state of an equal superposition of 0 and 1. And so the amplitudes are the root of 1/2. And of course, if you square those amplitudes, more correctly, squaring the absolute value of those amplitudes, then you get 1/2 probability of 0 being measured, 1/2 probability of 1 being measured. And then the blocks indicate, again, 50% probabilities. There's also a mark over here, it's the plus ket. And the plus state means it's a particular state, and that's the state that this is in. I'll show you that on the block sphere in a second. So here we are. Here's our circuit. We start out with 0, but we want to get into this state. And if you've studied like Hadamard gates, you'll know that there's got to be a Hadamard gate in this chest. So I'm going to pull it out and wield the Hadamard gate and put it here, and notice that then it puts the 0 into an equal superposition of 0 and 1, equal likelihood of being measured as either one. There's also here, I don't know whether you've dealt with the block sphere very much, but this is a very pixelated version of the block sphere. And using a block sphere, you can visualize in 3 dimensions 1 qubit. I'd like to go to this visualization of a block sphere that you can get to, by the way, in this presentation, just going that I just showed you, that's on that page. On one of the pages is a link to this block sphere visualization. And so we started out in 0, in the state of 0, 0 being at the top of the block sphere, 1 being at the bottom of the block sphere. And the challenge was to make it in an equal superposition and actually getting to this state, this plus state. If I take this H gate and apply it, then it turns that 0 into an equal superposition. Actually, anywhere on this equator is an equal superposition of 0 and 1, because it's halfway between the 0 and the 1. And this particular place on the equator is the plus state. And that's where we wanted to get, here at the plus state. That was the objective. And so we've accomplished that objective, and we can go to the next one. I think I have time maybe for one more room here. And so now, instead of getting to an equal superposition that at the plus state, it wants an equal superposition on the minus state. And you recall, if you look at that, that's on the back of the Bloch sphere here. And so how do we make this quantum state, how do we get it to the back of the Bloch sphere? And so let's see what things that we have to work with. Well, we have an X gate and we have an H gate. So we know that we need to put those on this circuit, but in what order do we put them on that circuit? So that's the question. Let's see, if we put the H gate on there first, let's say, we know what would happen. It would end up in the plus state. And then if we put the X gate there, well, nothing happens. Well, why doesn't anything happen? Why didn't it solve the puzzle? Why didn't it move off of the plus state? Well, let's go back to the Bloch sphere. We'll go back up to 1. Remember, we put an H gate on there. We ended up here. But then we put an X gate. X gate rotates 180 degrees around the x-axis. Or if you like to work with radians, it's 2 pi radians around the x-axis. But the state is right on the x-axis. So rotating it doesn't change anything. But if I put them on the other way, maybe do the X first, which the X doing it this way rotates around the X-axis, which is going to put it to the bottom of the Bloch sphere. And then I'll put the H gate here. The H gate solves the puzzle. And what's happening with that H gate is that's going to move it from here to there. And before I leave you, I'll just explain the physical representation, or the geometric representation of the Bloch sphere on the H gate. So we saw that the X gate rotates, pi radians around the x-axis, and the same thing with Y and Z, by the way. It rotates 180 degrees around those axes. The H gate, what it does is it actually rotates around an axis, or a line that is where the x-axis and the z-axis bisect. And so I'm looking right down straight into the Bloch sphere on the axis that it rotates. So we see, if we do an H gate here, it's rotating on that axis. And if, remember when the state was here at the 1 and I did an H gate, it rotates on that same axis. And so an H gate turns a 1 into a plus on the plus state there, and it turns a 1 into the minus state. And so when we go back here, we see that the state is back there on the back of the Bloch sphere on the minus state, and that we solved the puzzle. And then I could go through the next one, and then this one has us get to that minus state in another way using different blocks. So my challenge for you then is, here we are on we're level 1, room 6. My challenge is to you independently go through all 16 rooms on level 1, and then go into level 2 and go through all 16 rooms, in which you'll learn more about the fundamentals of quantum computing, as well as the ideas of quantum logic gates. And it'll take you right up to this algorithm called Grover's algorithm. So I'll leave you with that. Thanks for your attention and participation. And I guess if you have any questions, please let me know, or let me know offline at my at the contact information that I gave you.
Thanks so much, James, for this. And just for people who may have joined late, this is James from IBM Quantum Education. He was showing QxQ blocks, which are some fun games that you can play to practice out your quantum skills. We wanted to have James present today essentially as a way to show you that over winter break, which will be coming up in a few weeks, there's still resources online that you can continue to practice out your skills. So thank you so much again, James. We really appreciate it. If any students were struggling with that or didn't understand all the concepts, it's 100% okay. This is just a preview of also some things that we'll be learning in the next few weeks, and then obviously next semester as well. And with that said, I'm going to turn it over to Amir, who's going to start our lecture series on mathematics for quantum.
Okay, thank you very much.
Thanks, James.
Thanks, James. Okay, hi everyone. So again, it's been a few weeks, but I'm Amir, and today I'll be talking about mathematics for quantum. And actually, this lecture will help you get a better grasp of some of the concepts that we just saw in QxQ blocks, which is a fascinating thing. I would highly encourage all of you to go and explore a little bit. Okay, so with that, today we are going to be talking about the Dirac notation, inner products, and quantum operations, and mainly Hermitian operations and unitary operations. So off the bat, these words might not make sense to you. So we're going to go step by step slowly, and we're going to make sure that we know why we need to learn, these concepts. So I would like to start with the Dirac notation, or it's also commonly referred to as a bracket notation, which allows us to abstract away parts of the complicated underlying math for quantum mechanics. So in the previous lectures, we talked about linear algebra, and today I'll discuss how you can represent quantum states as vectors and quantum operations as matrices. The Dirac notation is a very powerful tool for not having to write out massive vectors and matrices all the time, and just be able to do some of these operations much faster. Okay, so with that, let's just do a quick review. So again, we talked about how bits can have a value of 0 or 1, and there's an equivalent for qubits, which is this sign here, the ket 0 and ket 1. And here, the symbol is a ket, and it indicates that we're talking about a quantum state instead of a classical state. So whatever is in between the this ket is a quantum state. So if we have the classical, QxQ, we can make that quantum by simply just putting it in a ket. But what does that really mean, actually? So a ket can be represented as a column vector. And let's start with 0 and 1. Again, the two building blocks of a quantum bit. So ket 0, I can write as a column vector with 2 entries. The top one is a 1, and then the bottom one is a 0. And ket 1, I can write that as a column vector with a top entry of 0 and a bottom entry of 1. Simple as that. And again, just a reminder, these are equivalent to when your bit has a value of 0 and your bit has a value of 1. In this case, your qubit has a value of 0 and your qubit has a value, or your qubit has a value of 1. And you can represent these with vectors. So again, the main reason why we went through linear algebra these past couple of lectures, well, I guess not the last 2 lectures, but before that, was because we can represent quantum mechanics using vectors and matrices. And now we're going to see them in action. So again, let's just do a quick recap of quantum superposition. So in quantum mechanics, objects can be in 2 states at once. And again, an example of that, just rough big picture, is the Schrodinger's cat, where the cat is, we put the cat in a box, we seal the box, and there's a mechanism that kills a cat with 50% probability and does nothing with 50% probability. And the question poses, is the cat dead or alive while the box is still sealed? And of course, we said that the cat is in a superposition of both dead and alive at the same time until we open the box, which is called a measurement, and we'll get to that in a little bit. But again, the general point is that in quantum mechanics, objects can be in a superposition of two states at once. And a qubit, a quantum bit, is a quantum object, so it can be in a superposition of zero, state zero or ket zero, and state one at the same time. And this is how we show it. So this is, again, a recap from the second lecture that we have. So here our quantum state is psi, or let me just write this as psi, and then it can be in a superposition of of zero with a coefficient alpha in front, and in one with a coefficient of beta in front. And again, we'll go back to what these alpha and beta means, but just so that we can represent it. So how would I write psi as a column vector? Okay, so let's see. In this case, I said psi is equal to alpha times the state zero, which I can write as 1, 0, plus, oops, fix that, plus beta times the state 1, which I can write as 0, 1. So I can multiply this scalar by this vector, and what I end up with is alpha 0 here. And then I can also multiply beta by the corresponding vector. And what I'll end up with is 0, beta. And of course, I can add two vectors together. I'll just add the top element to the top element and the bottom element to the bottom element. So here I end up with alpha on top and beta on the bottom. So again, there are two different ways of representing a quantum superposition. One is, I can write it in the bracket notation here using kets, which is totally fine. And the other way is that I can write it in terms of a vector. So again, the state alpha 0 plus beta 1 is equivalent to having a vector with alpha as the first entry and beta as the second entry. So let's do a few practices. So if I tell you that I have a state psi, which is 1 over square root of 2, 0, plus 1 over square root of 2, 1. What is the vector representation of this? And again, remember, we're going to have two entries. So what is the top entry and what is the bottom entry? Maybe take 20 seconds to work through this yourself, and then I'll write it down. Okay, so let's do this step by step again. And as you get better at this, you probably can skip a few steps, but just for the sake of practice. So I have 1 divided by square root of 2 times the 0 state, which again, I can write as 1, 0, the vector 1, 0, plus 1 divided by square root of 2 times the 1 state, which I can write as the vector 0, 1. And now when I add these two together, I get 1 over square root of 2 on the top and 1 over square root of 2 on the bottom. So yeah, nothing too crazy. Okay, now let's go the other way. If I tell you that my psi is equal to 1 divided by square root of 3 on the top, and then square root of 2 divided by 3 on the bottom. What is this in bracket notation? So with when we have some ket 0 and some ket 1 component, what are the coefficients? And again, take 20 seconds to go through this yourself. Okay, so I'm gonna break this vector down to a sum of two vectors. So I will write this as 1 divided by square root of 3 times the 1, 0 vector plus square root of 2 divided by 3 times the 0, 1 vector. So far so good. I can do that. I just simply broke down the vector. And then again, if you guys remember, what I told you is that this 1, 0 vector is just a 0 state, the ket 0. So this is equivalent to 1 divided by square root of 3 times ket 0 plus, and again, this coefficient doesn't change, 2 divided by square root of 3. And this 0, 1 state is the ket 1 quantum state. That. So again, the whole point is that you can go from the bracket notation, like representing a quantum state with kets, to representing it with a column vector, and vice versa. You can go from representing a quantum state with a column vector to representing it, with kets. Okay, so with that, let's move on to the next thing. So now I'm going to introduce a concept of a bra. So a bra can be represented as a row vector. And again, just you guys have learned what complex conjugates are. So the bra is a complex conjugate of a ket. But what do I mean? So again, let's look at a concrete example for this. So we had the zero state, ket 0. Now let's look what bra 0 is. So bra 0 is a row vector where the first entry, again, is 1, and the second entry is 0. And bra 1 is, again, similar to the bra 0 is just going to be 0 on the first entry and 1 on the second one. And in general, if you have, some state, actually, maybe let's go on to the next slide for you. So if you have, a state psi, where psi is equal to alpha 0 plus beta 1, then the bra of psi is going to be equal to alpha complex conjugated times bra of 0, or bra 0, plus beta complex conjugated times the state, bra 1. And again, you'll get more comfortable with this as we go throughout the lecture and see more practice. But just for the sake of practice. So if I tell you that I have a state psi is equal to, again, square root of 1 over 2, 0 plus square root of 1 over 2, 1. What is what is the bra of psi? And again, write this both in terms of bracket notation and as a row vector. And again, take 30 seconds to work through this yourself, and we'll go through it together. Okay, so let's start by writing this in the bracket notation. Again, just like if we look at the recipe that I wrote, on top here, the first part, 1 over square root of 2 is a real number, so the complex conjugate doesn't change anything. So I'm going to have 1 divided by square root of 2 times the bra of 0 plus, again, and 1 over square root of 2 is also a real number, so the complex conjugate doesn't change it. Plus 1 over square root of 2 times the bra of 1. And again, I can write this as a row vector by simply, writing the 1 state as 1, 0, and then, the 0 state as 1, 0, and then writing the 1 state as 0, 1, which then gives me 1 over square root of 2 and 1 divided by square root of 2 as the entries. And now let's look at another number. And now I'm going to actually start you guys off no, sorry, another quantum state. Now I'm going to start you guys off with writing my quantum state as a column vector. So I'm going to start off by, with this state. So now the state is 1 divided by square root of 2 as a first entry, and then I divided by square root of 2 as a second entry. And what I'm going to ask you to do now is to find what the bra of psi is. Again, both in terms of a column vector, or sorry, a row vector in this case, and with the bracket notation. So take 30 more seconds to work on this yourself. Okay, so as I mentioned earlier, a bra is the conjugate transpose of a ket. So now let's use that approach to figure out what this state is, what the bra of psi is. Okay, so first I will transpose the state. So I have 1 divided by square root of 2 on the top. Now it's going to be, again, that's still going to be the first entry here. And the I divided by square root of 2 is going to be a second entry. The biggest difference here is that instead of having a column vector, we have a row vector. So we just switched our rows and columns. That's the transpose part. And now the next part is for me to take the complex conjugate. So the complex conjugate of 1 divided by square root of 2 is the same thing because it's a real number. However, the complex conjugate of I divided by square root of 2 is negative I divided by square root of 2. And again, if you remember, when we take the complex conjugate of the imaginary part, we just put a negative in front. So in this case, I is an imaginary number, so I divided by square root of 2 is an imaginary number, so the complex conjugate of it will just be negative I divided by square root of 2. Okay, so this is how we would represent this, the bra of psi as a row vector. Now let's try to write this using the bracket notation. So here again, I'm going to break it down a little bit. So I have 1 divided by square root of 2 times the 1, 0 row vector. And over here, I'm going to have minus I divided by square root of 2 times the 0, 1 row vector. Again, as we discussed earlier, the 1, 0 row vector is just the bra of 0, and then the 0, 1 row vector is just the bra of 1. And just for the sake of completeness, I'm just going to write the psi here as like in the bracket notation so you guys can see it. So we had 1 divided by square root of 2, 0, plus I divided by square root of 2 of 1. And again, just to reiterate, so we started with the quantum state ket of psi, which was this was a notation, and we found out what the bra of psi is, again using 2 different methods, both using the vector notation and using the bracket notation. Okay, so let's move on to the next slide now. So now we're going to talk about what an inner product is, and we use inner products to find the overlap between 2 quantum states. And actually, the reason why the bracket notation is called, bracket is simply because we have, a bra. Again, here we have bra of psi, and then a ket. In this case, it's a ket of phi. And when we put them together, we get a bracket. So let's look at an example. If I have let's say, actually, we're going to have plenty of examples on the next slide. So let's just go with that. So let's try to do these one by one, and I'll get us started by, doing the very first one. Actually, yeah. So here, it's as if I have the bra of 0 times the bra of, the ket of 0. The bra of 0 is 1, 0. Let me fix that real quick. And then times the ket of 0, which is, a column vector now, with the top entry being 1 and the bottom entry being 0. Now, what do I get here? Well, this is a vector multiplication. So the result is going to be, the first element of the column vector times the first element of the row vector. So I get, 1 times 1 plus the second element of the column vector times the second element of the row vector. So I get, 0 times 0 here. And this gives me a 1. So the inner product of 0 with 0 is a 1. Okay, now I'll give you 20 seconds to try to find the inner product between 1 and 0, or rather to find the bracket 1, 0 here. And I will get you started by writing down the vector representation. So here we have 0, 1 times 1, 0. Actually, maybe I should, launch a poll here to see if, you guys could tell me, like, what the output is for these. Okay, so let me write this down for you. And again, the options are probably going to be 0 or 1. So here again, I multiply this 1 here by the 0 there, so I get 1 times 0 plus, and then the 1 over here times the 0 over there. So times plus 0 times 1, and this gives me a value of 0. Okay, now let's move on to the next one. Now I have the bra of 0 with the ket of 1. And again, the bra of 0 is going to be 1, 0. And the, let me fix that. And the ket of 1 is going to be the column vector with a 0 as the first entry and 1 as the second entry. And again, it's all the similar thing over and over again. So here we multiply, 1 by 0. And then we add it to multiplying, this 0 by this 1. And we get a 0 here. Okay, and finally, let's look at what the overlap or the inner product of 1 is with itself. So I have the ket or the row vector 0, 1, and then I'm going to multiply it by the column vector 0, 1. And I'm going to have 0 times 0 plus 1 times 1. And this gives me a 1. So again, it's as simple as multiplying, finding the inner product at the end of the day is as simple as multiplying a row vector by a column vector. Just that. So now let's look at something more complicated. Now, what if I have the state psi alpha 0 plus, again, beta 1, some arbitrary state psi, and I'm trying to find the overlap of, let's say, the state 0, which I'll show as bra 0 with ket psi. Well, let me expand this a little bit. So I said that I have here bra 0, And then it's as if I'm multiplying it by ket psi, which I'm going to write as alpha 0 plus beta 1. And now here's where we use a property that's called linearity, and it's the linear part of linear algebra. That if I have something like this, I can write it as alpha alpha times 0, 0. So this bra 0 acts on ket 0 here and also acts on ket 1 plus beta 0, 1. And again, this is very similar to what you've already seen over and over in high school algebra. Is that, for example, again, going away from the quantum world, if you have x times, let's say y plus z, that is equal to x times y plus x times z. And this property is called linearity. We'll see it again, but just remember that for the bracket and for the inner product, it works the same as what you're accustomed to in algebra. Okay, and with that being said, so if we go back to the previous slide, and again, this is something that hopefully you'll eventually end up memorizing, but it's just that the simple part is that with the 0, 1 state, their inner product with themselves is 1, and the inner product with the other ones. And the inner product of 1 with 0 or 0 with 1 is 0. So using that trick that we learned, here, the inner product of 0 with 0 is 1. So I have alpha here times 1, and then beta times 0, which just gives me alpha. Okay, so far so good. So now let's look at some other states. So then now let's make things a little bit complicated. Like now let's look at the inner product of two superposition states. So let's say I have again state psi, which is equal to 1 divided by square root of 2 times 0 plus 1 divided by square root of 2 times 1. And then I have the state phi, which is 1 divided by square root of 2, 0 minus 1 divided square root of 2, 1. And now I ask you, what is the overlap or the inner product of psi with phi? Oh, let me fix that again. With phi. And maybe this is a little bit more complicated, so take a minute and try to work through this yourself. But again, remember, you can, the same properties that hold for algebra will hold for the inner product just because it's a linear system. So take a minute and work through this yourself. And for the second one, we're going to do it in two ways. So we're going to do it using the bracket notation, which is something that hopefully you'll get comfortable with. And then we're also going to do it just using vector multiplication. Okay, so maybe let's start by doing this using vector multiplication. So here I have the bra of psi, which I can write as, again, a row vector, 1 divided by square root of 2 as the first entry and 1 divided by square root of 2 as the second entry. So this is what we've already seen. And I'm multiplying it, or I'm taking the overlap with a column vector now, since phi is a ket, with 1 divided by square root of 2 as the first entry and minus, fix that, and minus 1 divided by square root of 2 as the second entry. And yeah, so again, same as before, it's the same idea. So over here, I multiply, the first entries together, and I get 1 divided by square root of 2 times 1 divided by square root of 2, which is 1/2 here. And then I add the result of multiplication of the second elements. So here I have 1 divided by square root of 2 times minus 1 divided by square root of 2, which gives me minus 1/2. And this gives me 0. So the overlap between these two superpositions is 0. They are, you can think of them as being perpendicular to each other or being at a right angle. Now let's do this the second way, using the bracket notation that we just learned or went through. So here I have bra of psi, which I can write as 1 divided by square root of 2 times the bra of 0 plus 1 divided by square root of 2 times the bra of 1, right? And then it's as if I'm multiplying this by the state phi, which is 1 divided by square root of 2 ket of 0 plus, minus 1 divided by square root of 2 ket of 1. And similar to multiplication, we're just going to go one by one, in again, normal algebra variable multiplication. So I'm going to have 1/2 overlap of 0 with 0 plus 1/2 overlap of 1 with 0. Then it's going to be minus 1/2, because here I'm taking the 1 state here and then the 0 state here, and the coefficient in front of here is -1 divided by square root of 2. 0, 1. And then I am also going to have minus 1/2 the ket of 1 with 1. Because again, 1 divided by square root of 2 bra of 1 times times -1 divided by square root of 2 ket of 1. Okay, so let's go through these. So again, as you guys remember, the overlap of 0 with 0, or the inner product of 0 with 0, is just 1. So I'm going to have 1/2 here. This is 1. This one will be 0, because the 0 state and the 1 state have no overlap. Same over, 0 here. Same over here as 0 here. And then the overlap of 1 with 1 is 1. So I'm going to have 1/2 plus 1/2 times 0 minus 1/2 times 0 and minus 1/2. So I mean, of course, these are 0, and then I have 1/2 minus 1/2, which gives me 0. So again, these are two different approaches. You can either choose the bracket notation or the matrix multiplication or vector matrix multiplication, and they will lead to the same result.
Hey, Amir, before we keep going, this was a question from a student, can you just say more about what it means when two superpositions overlap? Maybe more conceptually.
More conceptually, well, I guess we will see that also, further along, but conceptually, if they overlap, they must be the same thing. So again, the idea of the overlap is how similar are your two states. If they exactly overlap, give you an inner product of 1, that means that they're the same state. If they have an inner product of 0, it means that they have no overlap whatsoever. So, they're perpendicular, or, we're going to have another name for it, I think, in the coming slides. And, you can basically figure out exactly what is the overlap between your two superposition states by taking the inner product.
Perfect. And there was one other question, since you mentioned linearity, that we might come back to, but is there something in quantum computing that cannot be linear, or does everything obey the rules of linear algebra?
Everything that we are going to do for this course, assuming a perfect system, is going to be linear. So and that's the beauty of quantum mechanics, is that you can explain it with vectors and matrices because operations are linear. Again, there are advanced areas of research into some potential non-linearities in quantum computing. Sorry, not quantum computing, even quantum mechanics at like very high levels. But as of now, that does not apply and is not relevant for quantum computing.
Cool. Thank you.
Sure. And that was the second one, especially, was a really good question because yeah, it's something that we take for granted and it makes our lives easier, but it doesn't have to be necessarily that way. Okay, so now, actually, that was a great segue. So now we're going to talk about two definitions. So the first one is that, two states, phi and psi, are orthogonal. Orthogonal means perpendicular, but we refer to, perpendicular states as orthogonal in quantum mechanics, in linear algebra, if their overlap is 0. And again, the example, let me go back a slide, is, the states psi and phi here were orthogonal to one another because their overlaps were 0. Or, another example is, the state 0 and 1. Okay, this and 1 are orthogonal again. This hand's struggling today. Again, because the overlap of 0, 1 is equal to 0. They don't overlap. And then the second definition is what normal means. And definitely, like, normal just means that, if the overlap of the state with itself is 1. And again, both 0 and 1 are normal. Again, meaning that the overlap of 0 with 0 is 1, and the overlap of 1 with 1 is also 1. Now, of course, they can have superposition states that are also normal. In fact, all valid quantum states are normal. So this is the one property that you have to remember. And again, if we just flash back, like when I was writing the state, for example, psi is equal to 1 divided by square root of 3, 0 plus 2 divided square root of 2 divided by 3, 1. The reason why I chose the coefficients the way that I did was to make sure that the overlap of psi with itself is 1. And in fact, maybe I actually use this opportunity as a practice. So, take 30 seconds and tell me what the overlap of, this psi with itself is. I mean, I spoiled it away, but maybe do it as a practice just to see that it makes sense. Okay, so let me start writing this out. Again, I'm probably gonna, I'm more used to using the bracket notation, and this is something that I hope that you guys get better at as we go along in the course. But for the purpose of practice, I will just be writing everything in the bracket notation from now on. So here we have 1 divided by square root of 3 times bra of 0 plus square root of 2 divided by 3 bra of 1 times, again, psi, which is, we have the definition up there. So 1 divided by square root of 3 ket of 0 plus square root, okay, this is not writing now. Square root 2 divided by 3 ket 1. And again, if we go step by step as we did it before, this is, so I multiply the first element of this parenthesis with the first element of the other parenthesis. So that gives me 1/3, 0, 0. And then, the first one here times the second one there. That gives me square root of 2 divided by 3, 0, 1. And then the second element here times the first element there, it gives me, again, same thing. Well, square root of 2 divided by 3, and this time it's 1, 0. And then finally, I do the second element. So I get 2/3, 1 overlap with 1. And again, as you all are an expert in this now, we know that this is 0, and this other state is also 0. This overlap is 1. This overlap is 0. And this overlap is 1. I get 1/3 plus 2/3, which gives me a perfect 1. And again, so, therefore, the psi that I have up here is a normal state. And again, all quantum states, in the absence of noise in a perfect quantum world, are going to be normal. Okay, now let's talk about measurement. Actually, we'll see how measurement we can also describe what happens when we make a measurement with the mathematics that we've learned so far. So the idea of measurement is that if you have a quantum state that's in a superposition of 0 or 1, or you can think of your Schrodinger's cat that's in a superposition of dead or alive until you open the box. Once you open the box or measure the qubit, the quantum state will collapse into either 0 or 1 for the qubit, or dead or alive for the cat. So essentially, your quantum cat or your qubit has to once you make a measurement, it has to decide if it's 0 or 1 or dead or alive, and then it'll be either. So it will be either completely 0, completely 1, or in the cat's case, completely dead, completely alive. And in a sense, measurement destroys your superposition and forces your quantum superposition to give you a classical state. And again, if we think of it in terms of our quantum qubit language, so if we have a qubit psi, which I can write as alpha times 0 plus beta times 1, once you make a measurement, it collapses the quantum state of the qubit psi to either 0 or 1. Now, in the past, we've talked about this. So for this state, if we have this state psi, the probability of measuring state 0 is alpha squared. But now let's see where that comes from. So what I'm telling you is that the probability of measuring 0 is going to be the overlap of 0 with psi, and then amplitude squared. Now, this amplitude squared comes from the fact that we care about the probability and not just the quantum amplitude. Again, this is similar to what we've seen earlier in the course. Okay, so let's look at this. So what is the overlap between 0 and psi? So I have, again, the overlap between 0 and alpha 0 plus beta, okay, this is problematic, and beta 1 here. Okay, parenthesis close, and then of course I'm squaring everything. So the overlap of 0 with 0 is 1. So I get an alpha here. And then the overlap of 0 with 1 is 0. So I don't have to worry about the beta term. And then everything is squared. And this is how we end up with the fact that when we measure our qubit that's in the superposition state, the probability of measuring 0 will be alpha squared. So that's a reason behind it, why we told you this fact a few lectures back. Now we can describe it using the math that we've learned. And similarly for probability of measuring a 1, so probability of getting a 1 is just going to be the amplitude squared of the overlap between 1 and psi. And again, same idea. So instead of 0, of course, I'm going to have a 1. And then I'm looking at the overlap with psi again, which is alpha 0 plus beta 1. There we go. Beta 1. And of course, it's amplitude squared. And again, if you remember, the overlap of 1 with 0 is 0, so I don't have to worry about the alpha term here, and the overlap of 1 with 1 is 1. So I end up with the absolute value of beta squared. And again, we over the past few lectures, with the exception of the Python lectures, we've been developing the mathematical tools that allow us to look at things using the bracket notation. And once we have those mathematical tools, we can exactly describe, how quantum mechanics is going to behave. And this is what we saw here. So, in lecture 2, we told you that if we have the quantum state above here, the probability of measuring 0 is alpha squared, and the probability of measuring 1 is beta squared. We didn't tell you exactly, why that's the case. And now here we're seeing why that is the case exactly. And again, if you remember, another fact from lecture 1 was that, one thing that we asserted was, alpha squared plus beta squared needs to add up to 1. Well, for multiple reasons. First of all, if you only have 2 options, either 0 or 1, the probability of measuring the first one and the probability of getting the second one need to add up to 100% or 1. But also now we see that this kind of ties back to why quantum states need to be normal. Because in order for a quantum state to satisfy this property, or for the concept of measurement on a quantum state to make sense in terms of the outputs, the overlap of a quantum state with itself needs to be 1, or it needs to be normal. Okay, so with that, let's take a 10-minute break, and then we'll be talking about quantum operations afterwards. Okay, everyone, we're just about ready to get started again. But before we move on, there are a few questions I would like to answer. So, Rachel, fire away.
Sure. Let's start with maybe the hardest one. Amir, what is noise and why did you mention it? Just at a very high level.
Right. No, so I like completely opened a Pandora's box. There actually.
Okay, we'll wait for the music to turn off. Akshay, you could also, if you want to jump in and try to take it, feel free.
The question about noise.
Yeah.
I don't know if I'm the best person to answer that, to be honest. But generally, we are treating this in all of this math. We're assuming that all of our gates behave perfectly and all of our states behave perfectly. But in any real physical system, there's going to be noise. There's going to be environmental noise. There's also some inherent noise in the system itself, and that can mess up your state. And that can, even if you predict the state to be something, the state could end up being a little bit different from that because of this external noise. So that's the general idea.
Perfect. Akshay, are you
Yes,
back?
yes. Sorry for the technical difficulties. Something with my headphone connection and going all over the place. So to Akshay is completely correct. So again, noise is a Pandora's box that I should not have opened. But just in short, our quantum system, when we have a qubit, it actually gets disturbed by the environment that's around it for any reasons, for any number of reasons, and that is called noise, or that leads to noise rather. And noise essentially leads to quantum computing error. And of course, we don't want errors, and bad things happen when we get errors. So similar to noise in classical computing, it's we have noise in quantum computing, except for that there are more noise sources because quantum superposition is very fragile.
Cool. Okay. A few people noted that 0 and 1 do not look perpendicular on the Bloch sphere. You say more about this.
That is a great question also. So there's a physicist Bloch sphere and a mathematical Bloch sphere. So in a mathematical the Bloch sphere that mathematicians use, a lot of times they are perpendicular, but the idea is that when we use a Bloch sphere, which again we will discuss in detail, we technically haven't introduced it yet, and we will further on in the course. The idea is that by having 0 and 1 on the poles, we can actually show how much a state is in 0 or how much is the superposition in the 1 state. So that's just a representation for convenience, essentially.
Cool. In some of the problems we were doing earlier, is there a reason that all of the denominators were in square root, or was it just a coincidence?
That was just a coincidence. So usually the whole coefficient in fun would be under square root, but since the numerators were often 1 for some lucky reason as a coincidence, the denominators were the only things under the square root. Whereas in general, the whole thing is under the square root.
Cool. Okay, and then last two questions, back to the Bloch sphere. Can 2 qubits be represented on a Bloch sphere?
So the Bloch sphere is meant for representing the state of one qubit. So 2 qubits can't be exactly represented on a Bloch sphere. And again, this is something that we will talk about next semester, especially. But there are correlations between 2 qubits that the Bloch sphere can capture. So the Bloch sphere is just for a single qubit.
Okay, and last one. How do I create an unequal superposition?
How do you create it? That's a good question. I mean, we can do that in lab, and we will create unequal superpositions down the road next semester, and we'll show you how to do that. But for now, most of the gates that we're comfortable using or that we've introduced to you guys create equal superposition. You could easily, come up with some valid quantum operation that creates any unequal superposition. Because again, it's a continuum, and you can choose any point of the continuum, and you can actually achieve that, or get very close rather.
Cool. We'll stop there with questions.
Okay, amazing. So, so far, the first part of this lecture, we talked about quantum states and the bracket notation. And quantum states are the inputs and the outputs of the quantum computer. Again, similar to how bits are the inputs and the outputs of your classical computer, quantum states, which describe qubits, are the inputs and outputs of your quantum computer. And quantum operations are actually, the stuff that performs computation in a quantum computer. So now with that, let's dive a little deeper and talk about quantum operations. So a quantum operation transforms one quantum state to another quantum state, just as simple as that. So when you act on a quantum state with a quantum operation, it gives you another quantum state. Nothing too complicated there. Now the idea is that we can represent them as matrices. And that's going to make our lives, much nicer. And this is actually why we did, 2 weeks of linear algebra, to give you guys a background, so that I can think of, these quantum states as vectors and quantum operations as matrices. And an example of quantum operations are quantum gates. So all quantum gates are quantum operations. Like in lecture 2, we talked about the X gate, which is the bit flip gate, the quantum bit flip gate, the Z gate, which is the phase flip gate, the quantum phase flip gate, and then the H gate, which is the Hadamard gate. We will be seeing these throughout the course, so don't worry if you don't remember them. Remember exactly what they are right now. And in fact, we're going to see them. We're going to see some of them on this next slide. So, some important quantum operators are the Pauli operators. There are 3 of them. So there's a Pauli X operator, which, has a matrix representation that looks like that. Sometimes we refer to this and write this as just X instead of sigma X, but either one's valid, and you'll be seeing either one in the quantum computing textbooks or papers that you read. Of course, then there's a Pauli Y operator, which has zeros on the diagonals, and then a negative I up top here and an I down there. Again, that's the Pauli Y operator, or sometimes just referred to as Y. And finally, we have the Pauli Z operator, or sigma Z, and sigma Z has a 1 on the first entry, the 0, 0 entry, and then a -1 on the 1, 1 entry, and the other entries are 0. So this is what quantum operations look like. The point of this slide is that all these quantum operations can be represented as matrices, and these 3 in particular are quite famous, and we'll be seeing them throughout the course and throughout quantum computing. So maybe let's look at an example now. So I told you guys what the Pauli Z operator is. Now let's see it in action. So if I have, if I have the sigma X operator and I apply it to the 0 state, what do I get? Well, I'm going to write this down, and we're going to go through this together. But for the next ones, I'll give you guys an opportunity to play with it yourself first before we go through the problems or the practices. So, okay, what I said is that the Pauli X operator is 0, 1, 1, 0, and then the 0 state is 0. This pen is struggling a little bit today. Okay, so now I have to multiply a vector by a matrix. Well, so the output is going to be a column vector with 2 entries, and the first entry is going to be this 1 times 0, and then plus 0 times 1, which just gives me a 0. And then the second entry is going to be this 1 times 1, which is a 1, plus 0 times 0, which is a 0. So I get the 0, 1 state out here, or the 0, 1 vector rather. And this is equivalent to the 1 state. And this is, so the Pauli X we've seen before. We introduce it as either sigma X or the X gate. And what it does is that it flips the state of the qubit. And that's what we see. So now we see the math behind it, actually. So when I applied this sigma x operator to the 0 state, I got the 1 state out. Now, as practice, let's do sigma x times 1 using the same approach. And again, take the 10 to 20 seconds, do it yourself, and then we'll go through it together. Okay, so again, we know what the matrix representation for sigma x looks like, or the Pauli x looks like. It's 0, 1, 1, 0. And now I'm multiplying it by a vector that has, or a column vector rather, that has 0 as a first entry and a 1 as a second entry. So in this case, the first entry, we have 0 times 0 plus 1 times 1. So I get a 1 on the first entry of the result. And then for the second entry of the result, I have 0 times 1 plus 1 times 0, which is 0. So I get so the resulting column vector is going to be 1, 0. And that is, if you remember, the 0 state. So this should be, you should also be familiar, you should almost be familiar with this by now, that when we apply the X gate, or the quantum X gate, or the sigma X gate, or the Pauli X, now they're all the same, different names for the same thing, it flips our qubit from the 0 state to the 1 state, and from the 1 state to the 0 state. Now let's look at another operator that we're familiar with, and that is the phase gate, or sigma Z, or the Z gate. So what happens if I apply the Z gate to the 0 state? Take 10 seconds, try to write, and let me actually write the matrix representation just in case you didn't catch it earlier. So the matrix representation for Pauli Z, or sigma Z, is 1, 0, 0, negative 1. And okay, for the 0 is 1, 0. So maybe take 10 seconds, try to do this matrix multiplication yourself, and then we'll go through it together. Okay, so the first entry is going to be 1 times 1 and 0 times 0. So that just gives me a 1. 1 times 1 plus 0 times 0. And here I have 1 times 0 plus 0 times negative 1, which gives me 0. And this is the 0 state. And again, if you guys remember, when we apply this quantum phase gate, or the Z gate, or again, Pauli Z, to the 0 state, it doesn't do anything. But now what happens if I apply, this gate that we have to the 1 state? And again, take 20 seconds to do this by yourself as I'm writing it down. So here for the first entry of the resulting vector, we get 0 times 1 plus 1 times 0, and that's a 0. And then for the second entry, we get 0 times 0 plus 1 times negative 1, which is a negative 1. And now if I were to write this in the bracket notation, this would be minus 1. So a negative sign in front of the 1 state. And again, if you remember from what we've seen in the past, and when you apply the Pauli Z operator to the 1 state, it adds a negative sign in front. And it doesn't do anything when you apply it to the 0 state. So this was just to get a general idea of how these work. And again, it's fairly straightforward. When you apply these operators to a quantum state, it's as if it's just doing a vector matrix multiplication. That's all there is to it. Now, quantum operations have a few nice properties. And again, this linear property, keeps on coming back all throughout quantum, like when we talk about math for quantum computing. So of course, the first one is that they're linear. And what do I mean by that? So let's say, I have a quantum operator. I'm going to call this A, just arbitrarily. And if I apply it to, a superposition state alpha 0 plus beta 1, it's as if I've applied this operator to every element of the superposition individually. And what that will look like is alpha times this operator A applied to the 0 state plus beta times, again, this operator A applied to the 1 state. Now let's do an example of this. So let's say I have my Pauli X operator, sigma X, and I apply it to the square root of 1 divided by square root of 2, 0 plus 1 divided by square root of 2, 1 state. What do I get? And take 20 seconds and then we'll go through this together. Okay, so here I have 1 divided by square root of 2 times sigma x 0 plus 1 divided by square root of 2 times sigma x applied to the 1 state. And if you guys remember from the previous slide, when we apply sigma x to the 0 state, we get a 1. And when we apply sigma to the 1 state, we get a 0. So the resulting state is 1 divided by square root of 2 times 1 plus 1 divided by square root of 2 times 0, the 0 state. And then, of course, you can switch these back and forth, so it doesn't change the initial state. Now, what if I apply a sigma z operator to the same superposition states? What superposition state? What do I get? And again, take 20 seconds, do this on your own, and then we'll go for it together. Okay, so it's the same idea as what we had above. So I have 1 divided by square root of 2 sigma z applied to 0 plus 1 divided by square root of 2 sigma z applied to 1. And sigma z applied to 0 doesn't do anything, doesn't change 0. So I have 1 divided by square root of 2 times the 0 state. And then the sigma z applied to the 1 state, gives you a negative 1. So I have minus 1 divided by square root of 2, 1. And something that again might be interesting, and we will see this coming back in the future, is that for this particular superposition state, applying sigma x didn't change anything. We applied sigma x to this superposition, and we got the same superposition out. Whereas when we applied sigma z, we got a different state out. So now there's a negative sign between the 0 part and the 1 part. And that is something interesting that we will see the applications for in the following lectures. But just to recap, the idea of linearity is that if you apply an operator to a superposition state, it'll act on each element of the superposition individually. And actually, as a side note, this is cool in the sense that if you think about it, like if you have a big quantum computer with 50 qubits and to the power of 50 superposition states, once you apply a single operator, a single quantum gate, it'll change all the 2 to the 50 superposition states all at the same time in parallel with a single operation. And that is actually, where some of these quantum speedups come from. It's this concept of quantum parallelism that comes from this linearity notion that we have. Okay, so the next part is that they can be composited. So let's say we have two quantum operators now, A and B. And if I apply them to psi, I can first apply B to psi and then apply A to the result. Or alternatively, I can multiply these operators together first and then apply the result to psi. Okay, so maybe let's look at an example for this now. So let's say, I have my Pauli Z operator and my Pauli X operator. So let's do, Pauli Z times Pauli X, times the zero state. Okay, so what do I get in this case? If I first apply Pauli, and let me maybe fix this here so it's not confusing. So if I first apply a Pauli X operator to the zero state, I get, well, Pauli X flips zero, so I get, so I have the Pauli Z left. I get a 1 here, and then if I apply the Pauli Z operator to this one state, I get a negative 1. Now, what if I do this the other way? What if I first multiply my Pauli Z by my Pauli X and then apply to 0? Well, so for this, let's actually maybe write things down in terms of matrices. So I'm going to make a side note here. So Pauli Z is 1, 0, 0, negative 1, and Pauli X is 0, 1, 1, 0. And here we have to do a matrix multiplication. So, and the result, so we're multiplying two 2 by 2 matrices together, and the result is going to be another 2 by 2 matrix. So the first entry is going to be 0 times 1 here, and this 1 times 0, that's going to be the first entry. So the first entry is 0. Now the second entry, the entry on the top right, is going to be the right entry here times the top entry here. And that gives me a 1. Okay, so let me maybe, now that I have that, I quickly erase what I drew around here. Okay, so now the entry on the bottom left is going to be the bottom entry of the first one times the left entry of the second one. And I get a negative 1 here. And finally, the bottom right entry is going to be the bottom entry here times the right entry of the second matrix. And I have 1 times 0, and then 0 times negative 1. So I get a 0 here. Okay, so if I apply sigma x by, sigma z by sigma x, I get, this matrix. So now I'm just going to copy paste the matrix right up here. So I have 0, 1, negative 1, 0. This is a new operation. And then I'm just going to multiply it by the vector for my 0 state, which is 1, 0. And the result is going to be, okay, so 1 times 0, 0 times 1, the top entry is 0, and the bottom entry is 1 times negative 1, 0 times 0, and a negative 1 here, which gives me a negative 1 state. So this is a sanity check. So regardless of, where I draw these parentheses, I get the same result out. And that is the idea that quantum operations can be composited. You can combine the two, call them a single quantum operation, and then apply it to your quantum state, or you can apply each of them individually from, of course, from right to left. So B gets applied first, then A gets applied. Yes, Rachel?
Hey, back with a question. Students are asking, how can we have a negative ket? What does that mean?
Well, I mean, it's just that the coefficient in front of the ket is negative. So, you can have it's as if you have a -1 times your ket 1. Same way that you can have, 1 times your ket 1. Now, remember, the coefficient in front of your ket can be any complex number, and -1 counts.
Cool, thanks.
Okay, that was an easy question. And again, you will see the effects of this negative as we get deeper and deeper into the quantum computing. This is something that we don't see in classical computing. Like in classical computing, there's no meaning for -1 bit, like -1 times like a bit having the value of 1. But in quantum computing, this actually is the reason why we get quantum interference in some quantum speedups. And again, we will see this in action as we go along. Yep. And the third property of these quantum operations that I want to talk to you guys about is that order matters. So what I mean is, if I have, if I'm multiplying two operators, A times B, that is not necessarily equal to B times A. There are special circumstances that it could be an equality, but not necessarily. And this is a little bit counterintuitive from the normal algebra that you're used to, because in normal algebra, if you have x times y, that is equal to y times x. But it's not the case for quantum mechanics and linear algebra necessarily. And as a side note, just to give you guys a little bit of a sneak peek for next semester, this is the thing that leads to Heisenberg's uncertainty principle, where if you measure the position of a particle, you can't measure or you can't know the velocity at the same time, or vice versa. If you want to know the velocity of a particle, you can't know the position, which is fascinating. Okay, and again, let's look at an example in this case. So let's say I have sigma x, sigma z, and then times sigma z, and I apply this to the 0 state. What do I get? Also, I'm gonna go layer by layer in this case. So I'm gonna actually apply sigma z to 0 first, and then sigma x. So when I apply sigma z to 0, nothing changes. So I'll be left with sigma x applied to the 0 state, and this gives me a 1 state. Now let's switch the order of the operators. Let's look at sigma z times sigma x applied to the 0 state. And again, I'm going to do it layer by layer. So I'm first going to apply sigma x to the 0 state, which gives me a 1, and then I'm going to apply a sigma z to this operator, which gives me a -1 times the 1 state. And we can see that these two are not equal. And this is something that is a little counter to the normal algebra that we've learned so far, is that the order of these operations actually do matter. Okay, so with that, let's just do a quick review of what conjugate transpose means. So if you guys remember, the conjugate transpose, which we show with this dagger, is when you have a vector or a matrix, you take the transpose and then you take the complex conjugate, or you can do it the other way. You can first take the complex conjugate and then the transpose. So for example, if I have an operator A again, and the matrix form for this operator is A, B, C, D, then a dagger, and we usually use a dagger for complex conjugate. So a dagger is going to be equal to, okay, so let me do the transpose first now. So the transpose of this matrix is going to be A, C, B, D. And then there's going to be a star here for the complex. And then, then I just the complex conjugate of each element. So I'm going to have A star, C star, okay, B star, B star, and D star as my elements. So again, given A as this this ABCD matrix, A dagger, the matrix for A dagger looks like what we have over here. Now there are some neat properties that I'm not gonna prove here mathematically, but for example, if we have A times B, again, A and B are both operators, and I take the complex conjugate of this, so AB dagger, so the dagger will apply to each of them individually and it'll switch the order. So then I will have B dagger times A dagger. So it switches order. And now let's look at a quantum operator applied to quantum state. So if I have the operator A applied to the state psi, and I take the complex or conjugate transpose of this, I will get, so the conjugate transpose of ket psi is bra psi. We talked about it earlier, and we switch the order. So we have bra psi times the complex conjugate operator of A. And again, these are just some properties that are good to know for down the road, and we will see these and we will bring forces throughout the course. But I just want to introduce them here. And I know you've already seen conjugate transpose. Okay, so with that, let's talk about Hermitian operators. So again, you might ask, what are Hermitian operators? What's the point? So all observable operators are Hermitian. What do I mean? If it's something that we can look at and we can measure, it's Hermitian. And for example, position of particles, that's a Hermitian operator, because we can like, I can tell you exactly where my pen is. It's in my hand. So is momentum. And if you don't know momentum is just, we show it as P is equal to mass times velocity. So you can really think of momentum as velocity at the end of the day. So the momentum of objects is also a Hermitian operator because it's something that we can measure. We can measure the velocity of objects. And so is energy. Energy also has to be a Hermitian operator because it's something that we can measure. So that's all that Hermitian means. Now, the mathematical definition is, an operator is Hermitian if A is equal to A dagger, or the operator is equal to its own conjugate transpose. So let's look at an example of a potential Hermitian operator. So sigma x, is this Hermitian? Let's see. Well, sigma x is equal to 0, 1, 1, 0, right? And what is sigma x dagger? Okay, well, let me do the transpose of this first. So the transpose of sigma x is 0, 1, 1, 0. If you guys okay, so if you guys remember, the transpose flips these two elements and keeps the diagonal elements the same. In this case, they're equal. And then, of course, there's a star here, and then all these numbers are real, so the complex conjugate of real numbers will just be the same. Okay, so the conjugate transpose of Pauli x is equal to Pauli x, or Pauli x is equal to its own conjugate transpose. So therefore, it is Hermitian. meaning that this operator is something that we can actually go in lab and measure, which is cool. And again, we will see this when we talk about spins and the Stern-Gerlach experiment at the beginning of next semester, when we actually do proper quantum mechanics. Okay, so this was a definition of a Hermitian matrix. Now let's again switch gears to something that we talked about during the first lecture and the second lecture, and that's the concept of reversibility. So if you guys remember, the idea behind reversibility is that given the outputs of a gate, or you can think of it as an operation, can we determine what the inputs are? And if we can determine what the inputs are, then the gate is reversible. So reversible gates or operations preserve all the information, whereas non-reversible gates, or a non-reversible gate loses some information. And if you remember, we mentioned that, because of this information preservation, we need all of our quantum gates to be reversible. Because otherwise, the noise that we get due to the loss of information, again, the word noise is making a comeback here, will destroy our superposition and our quantum information. Now, with that, unitary operations are operations that are reversible. Or in other words, all reversible quantum operations are unitary. And an example of that is time evolution. So again, given no noise, if something changes with time, and let's say we let time pass for a second, we can reverse time and go back to the initial state. Again, this is assuming no noise, no loss, nothing. So if we move time forward, we can also move it backward and retrieve the initial state. And that is a picture that I want you guys to have in mind for unitary operators. It's something that you can either go forward in time, and then you can move back in time and get to the initial state. So with that, all reversible operations are unitary. So all quantum gates have to be unitary. And again, this is something that I want to emphasize. So, again, if you guys remember earlier, we said that all quantum gates are quantum operations, but it doesn't work the other way, because, your quantum gates have to be unitary, and the unitary operators are only a subset of possible quantum operations. And the definition of a unitary operation is, if you have A and you multiply it by A dagger, or its conjugate transpose, it's going to give you the identity. And same if you switch the order. So if you multiply A dagger by A, it'll still give you the identity matrix. Or another way of course writing this is that A dagger is equal to the inverse matrix of A. So let's look at an example. I'm gonna maybe talk about this gate, this S gate, which is something that we haven't introduced, but I just want to use it as an example here. And what this is we have 1 and -1 on the diagonals, and then 0 on the off diagonal elements. So what is the the conjugate transpose of this S gate? So S dagger is going to be equal to, I'm first going to look at, again, I'm first going to take the transpose of this matrix, and then I'm going to take the complex conjugate. So the transpose of this S matrix, this S operation, is just the same thing, since there's 0 off, the off diagonal elements are 0. Of course, now there's a complex conjugate sign on top. Okay, now the complex conjugate of 1 is a 1, and then of course same with 0. But the complex conjugate of I now, or negative I, becomes positive I. Because again, as a reminder, when we take the complex conjugate of an imaginary number, we just put a negative sign in front. Okay, so let's see, what is S times S dagger now? Maybe take 20 seconds, try this, and then while you're at it, also try S dagger times S. And figure out what that is also. Yeah, let's take 20 seconds for these. Okay, so let me start by writing these down. So S is 1, 0, 0 minus I, and S stagger is 1, 0, 0 I. Okay. So let's see. First, let's look at the top left element. I have to multiply these two rows and columns, and I get a 1 up here. Now top right, which means that I will need to do top here, right here. I get a 0 here. It's 0 times 1, and I have I times 0. Both of them are 0. Now bottom left, so bottom here, left here, I again get a 0. And now bottom right, so it's right on this one and bottom on this one. And I have 0 times 0, which is 0, and I have I times negative I. So if you guys remember, I times I gives us -1, and I have a negative in front, so I get a 1. And that is the identity, which we show as I. And it's almost a similar story for S stagger times S. So I have, in this case, it's 1, 0, 0 I times 1, 0, 0 minus I. And the first entry is going to be these two multiplied, which gives me a 1. I'm going to skip the off-diagonal entries and just trust me that they're 0. And then the final entry is, when we multiply this row by this column. And again, I have negative I times I, which gives me a 1. So this one's also the identity. So for example, this S is a unitary operator. S is unitary. And again, the idea of unitary operators are that they're quantum operators that are reversible. So if you apply them, there's something that you can apply that reverses the effect. And that thing that you can apply is a conjugate transpose. So with that, I would like to wrap this lecture off and pass the platform to Kira for announcements, or Rachel.
Thanks so much, Amir. So we'll be continuing next week as well with the same lecture series, Mathematics for Quantum. I have 2 announcements for this week. One, some of you have seen that we have opened up applications for second semester of this course. If you are attending this lecture and already enrolled in semester 1, you do not need to apply for semester 2 or automatically enrolled in semester 2. Please, though, applications will be open through December 13th, so please encourage your friends to apply. We will have applications open for the next week, so please make sure you're sending that out. Second, everyone is required to fill out the lab form or lab preference time for semester 2. You should have already received communication about this via Canvas, so please make sure that you fill that out. It is required for everyone to fill out and I have been notified you will not get an email. It's on Canvas though, so please make sure you go to Canvas. It's posted there, and fill out your preference time for your lab for second semester. With that said, have a great week, everyone, and we'll see you in your labs this week.